Thanks very much. I'm going to talk about a very, very particular problem, but I would like first to motivate where it comes from, because there are people in the audience with various backgrounds, so you have to excuse me if I'm going.
Are you turned on?
Oh, yes. Okay.
Okay. All right. Okay. So I'm going to motivate the problem to explain where it comes from, and then I'm going to present hopefully the full solution. It's based on an open problem I posed here at the beginning of the workshop. Bruce was here and some other people, about the representation of Skorokhod reflection mapping. And my colleague and friend Venkat Anantharam became very interested in it. I was half interested, so he pushed me and we solved it. In fact, that's what I'm going to do now, is I'm going to present the solution of it. So it's a content of a preprint that's called Integral Representation of the Skorokhod Reflection. And we use basically order-theoretic properties, and this is something we had done in the past with Venkat in 2005. Is a paper we published in a journal called Order, 2005, that's called Regulating Functions on Partially Ordered Sets. So I don't know if I will have the time to go through everything, because I'd rather present the solution, something you can take with, perhaps you can generalize it further. Okay, so Skorokhod reflection problem was introduced by Skorokhod in the early 60s as means of representing the solution of a stochastic differential equation with reflecting boundary condition at 0. Okay, so you can we can define Skorokhod reflection as follows. So we're given some function. First of all, I'm going to define Skorokhod reflection problem in one dimension. So I have a function which could be the path of a Brownian motion, for instance, the path of a Levy process, or any deterministic function that you like. The minimal conditions we want for these functions is that it is nice. It has left and right limits at every point. Okay, and by convention we can make it to be right continuous. And we seek to find a function L of t, which is, I will be calling it the regulator, such that when I add to x, I get a process, let's call it Q of t, that is non-negative for all t. And I want the function L to start from 0. I want L to be increasing, and by increasing I mean non-decreasing. And I want it to be in such a way that its points of increase are contained in the set of zeros of Q. So L cannot increase when Q is positive. So we can write this condition by saying integral of Q of t dL of t is equal to 0. So if we think of L as being a measure, it doesn't charge the points at which Q is positive. Okay, it's well known that the solution of this is the following, and it's one of the rare cases where you can write the solution explicitly. It's L of t equals minus infimum x of s minimum 0, 0 less than s less than t. So what is this? It is, we have the function x of t, let's say the function looks like this. As long as it is positive, nothing happens, L is 0, and as soon as it becomes negative, it starts following it, and then when it increases again, it remains constant, so it's the lower envelope of the function x with a negative sign, so flip it around to get the function L. So for instance, if x is a Brownian motion, the L that you get there is an increasing function which is singular with respect to the Lebesgue measure. I mean, the points of increase have measure 0. It's in fact is a perfect set. So we can have all kinds of possibilities for L. Now it's very easy to see that L satisfies this. Okay, that's obvious from the picture. You can make it rigorous if you like, but it's obvious that L stays constant whenever Q is positive. What is Q? Q is the difference between L and between the actual curve and the lower envelope. So that's what Q is. So that's obvious. It's obvious that L is increasing. It's obvious that it starts from 0. Okay. And in fact, L is unique. We cannot find any other function that achieves these properties. And one way to see that is by saying, well, if I had another L bar, let's say that satisfied the same thing, then if I take Q bar of t, Q of t minus Q bar of t squared, let's say, and which by the way is a function of bounded variation because x vanishes and therefore it's a difference of the two bounded variation functions, I can write it as an integral from, let's say, 1/2 that, integral from 0 to t of qs minus q bar s d qs minus q bar s, and because q minus q bar is equal to L minus L bar, I can replace that by L of s minus L bar of s, so that integral becomes q times L, so I have integral q dl, plus q bar L bar, q bar dl bar, minus integral q bar dl, minus integral q dl bar. Well, that's 0 by assumption, that's 0 by assumption, and so that's less than or equal to 0. And so the two things are the same. So that's one way to see the uniqueness. There is another equivalent way of formulating the Skorokhod reflection problem, which is order-theoretic, and it is as follows. Let me put that up and right here. My formulas are going to be less complicated than Ono's formulas. I'm sorry. So it works as follows. So let's say that we consider all functions L that map 0 infinity into 0 infinity, such that L of 0 is equal to 0, that are increasing, and when I add them to x, I get greater than or equal to 0. Okay, so let's call this set something. I don't know, let's call that script L. We can think of script L as being a partially ordered set, partially ordered by pointwise order. Okay, as such, it has a least element. That is, it has an element which is smaller than every other element of this set. And of course, it is unique, and this least element is L of t. Okay, so L with component-wise partial order possesses a least element, and this is given by this formula that I wrote above. Okay. Again, that's very easy to see. In fact, this is easier than the above if you write down the requirements. I'm not going to do that now. So how do we think of the Skorokhod reflection geometrically? I'm going to spend 5 minutes to show the geometry of this problem, which is also nice if you want to generalize it. Okay, so what's happening here? We have the interval, I mean the half line 0 infinity. Yes?
Are you saying a priori there should be a minimum because you just take the pointwise minimum of all infimum of all the functions?
I don't say a priori, this is something you can show. Yeah, it's not, it requires a couple of lines, which I'm skipping at the moment, okay? It's, yeah, I mean if you...
So you're using your construction of L?
In fact, this way you cannot, you don't even have to write the formula. You can guess it by writing down the pointwise inequalities, and that comes out. You don't even have to write the formula. This, if you pose the problem this way, the formula comes out. So it's a nice thing about it. So, so let's think geometrically. What happens here is we have, let's say we have a little, we have a very thin tube here, if you like, And inside the tube, so that's supposed to be the interval 0 infinity. Inside the tube, we have a bug, okay? And the bug moves up and down. All right, it performs a motion. Now the bug is very strong. There's a wall here, and if the bug hits that wall, it will push it down. Okay. So there is a motion that the bug, so we have two observers. One is the observer sitting down here, and one is the observer that's moving together with this tube there. Okay? The observer outside just sees the motion of the bug, which is x of t. The observer here sees q of t. Okay? What the bug does is does nothing to the lift as long as it moves, but when it touches this, it pushes it down. Okay? So we can take this this tube, I call it a lift or elevator, or whatever you want to call it, and put an upper boundary as well. So let's call it B. So you have a little bug here. You see the little bug performs a motion like this. Okay? And if the bug hits this up, it pushes it. Okay? It's very strong bug. Down, it pushes it down. So this is the free motion of the bug, that's x of t. The motion is perceived by the pedestrian. And there is a constrained motion q of t that is necessarily between A and B, that is seen by the observer who is moving along with the elevator. It's very difficult to write down an explicit formula between x and q.
So when the bug pushes the bottom barrier down, does the top barrier descend as well?
Yes, it pushes the whole thing. So the lift is a solid body, and it's just a rigid body, and it pushes it together. This can be relaxed. In fact, we can make these boundaries also depend on time as well and do other things. But that's the thing. So if we associate a process, a regulator L of t with the lower boundary and a regulator U of t with the upper boundary, then mathematically the problem becomes add something. So these are increasing processes. Add something and subtract something. And this acts, namely it increases only when the bug is down here. This is the position of the bug as seen from the moving observer. And this increases only when the bug is up here. Okay? So these are the requirements. That's the Skorokhod reflection problem. It has a unique solution. Okay? There is a formula that can be written down. And in fact, we had written the formula in the early 90s for a solution of a problem in communication networks. Back then. We had done that actually in discrete time. In continuous time, it was written in 2009 in a paper by Burzi, Kang, and Ramanan, 2009, in stochastic processes and applications. By the way, you will see very little probability in my talk, but all these things are used in probabilistic contexts. When I say the formula was written down, I don't mean to trivialize it. It takes several pages to write it down and prove the formula. It's a long formula, but I'm not going to show it to you. Okay, now let me go one step further with a geometric picture and give you what happens in many dimensions. In fact, I'm going to start with a network. I'm going to take the network that was used by Ono yesterday and write down the Skorokhod reflection problem for that geometrically.
Can I just ask, Takis, you're assuming some regularity on x, presumably?
I'm assuming that x, yes, it is a CAD-like function. So it has left and right limits.
You wanted a little bit of continuity.
That's all. Although, if we pose it in the order-theoretic manner, we can drop all assumptions.
But if you have your fixed tube,
yes,
then you kind of want to integrate out the time on the bottom and the time on the top to kind of see where you've got to be. And you don't really want this thing. So I mean, if x were everywhere discontinuous, for example.
Yes, it will. If x is that's right. So if x is continuous, what happens? Yeah, I have to say that it will. If the jump is larger than the remaining distance, it will chop the jump. The jump must be chopped exactly at that point in order to be minimal. Okay, so I'm skipping many things. Anyway, I'm going to concentrate only on continuous functions today. So just to show to people who come from another area how this is related to networks, let me take the picture that Ono had yesterday. I mean, it's just as a motivation. I'm not going to go to the level of detail of Ono because Ono had queues which had exponential service times. In this case, so they had two queues, and one was general service time, that was deterministic, all kinds of things. Here, I'm going to obliterate everything and take a macroscopic point of view. So imagine that this is a kind of queuing system, but I'm thinking of it at the level of fluids. So there is water flowing through these things, and associated to each box, there is a certain service process. So let's say here we are serving at a rate C1 of t. Here at the rate C2 of t, here at the rate C3 of t. In fact, let me denote by C1 of t the cumulative service process if the first Q was non-zero between 0 and t. Okay, so think of a rate C1 prime of t. Okay, that's not the actual thing that we're going to see because at certain points of time it may be 0 and we'll see less than that. There is a certain C2 of t and a certain C3 of t here. Okay, so the actual thing we're going to see is going to be less by an amount L1 of t here, which is the amount of unused worker service, L2 of t, and L3 of t here. So what enters here is C3 minus L3. This has to be chosen in a way that is always smaller than C3. And not only that, but the increments of this must be smaller than the increments of this to have an increasing function. Okay, so that's part of the requirement. That's C1 minus L1, that's C2 minus L2, and again you have C3 minus L3. So the content here, Q1, Q2, Q3, I can write the following equations. I can write that Q1 of t is equal to Q1 of 0, if I have some initial thing there. If everything is 0 to start with, there is nothing happening in the system because there's nothing that comes in. So I must assume some non-zero initial conditions, plus C1 of t minus L1 of t, sorry, C3 minus L3 minus C1 of t minus L1 of t. So I have this. And Q2 of t is equal to Q2 of 0 plus C1 of t minus L1 of t minus C2 of t minus L2 of t, and Q3 of t is equal to Q3 of 0 plus C2 of t minus L2 of t minus C3 of t minus L3 of t. So let me write these equations in a vector form. I will call Q of t the vector of these things is equal to Q of 0 plus C3 minus C1, I'm going to call it x1. C1 minus C2, I'm going to call it x of 2. C2 minus C3 is x3. So let's call this x of t. That's a vector. And then I have L1, L2, L3. What happens to L1, L2, L3? Well, let's write this way. L1 comes with the plus sign, so that's plus 1. There is no L2 here, so 0, minus 1. L2 comes with the plus sign, L1 with a minus sign, and it's a 0, and L3 comes with a plus sign, L2 with a minus sign, and that's 0. So, or you can write this thing, it's better to write that as L1, or L1 of t, times the vector 1 minus 1, 0, plus L2 of t times the vector 0, 1, minus 1, plus L3 of t times the vector minus 1, 0, 1. Okay, so these vectors are called reflection vectors, and L1 will increase only when Q1 is equal to 0, naturally, because that's the unused work. L2 increases when Q2 equals 0, and L3 increases when Q3 is equal to 0. The sum of the Qi's is constant. All these things vanish after I sum up, and so the sum of the Qi is equal to the sum of Qi of 0. So what do we have here? The geometry of the problem is I have a triangle. I mean, this is the positive orthant. This is the axis. If you like, Q1, Q2, Q3, 0, and that's the positive orthant that where the system lives. Okay, so that's an equilateral triangle. So we can think of that as a lift. So let's see, for example, I'll show you how the lift moves. I take a piece of paper. I just happen to have a square piece of paper in my pocket. Okay, I'll just fold it to make an equilateral triangle. You know how you make equilateral triangle? Well, you just fold it in the middle like this. Okay, I'm going to do origami geometry, which has more abilities than Euclidean geometry. Then I take this and fold it so that this point falls over here, this, and fold it so that this point falls over here again, and there I have your equilateral triangle. These are 60 degrees what I did here. Okay, so this is my lift here. Now if I draw the reflection vectors on this lift, the reflection vectors will be like this. There will be a reflection vector here, which is parallel to this, a reflection vector parallel to this, and here a reflection vector parallel to this. So these are my reflection vectors. They are constant on each face. Okay, and so you have your bug here that's performing a Brownian motion in here. If the bug goes and hits this, well, it's moving parallel to this reflection vector, like this. If it stops moving. If it moves away, then if it goes here, well, it starts moving this way. It goes away, and so on. So it moves always in either this direction, or this direction, or this direction. So that's how we can think. That's the geometry of the Skorokhod reflection. That's true in general. We can take any convex set, and to each point of the convex set associate a reflection vector. Actually, it's a little bit, it's not quite correct, because points like corners, we shouldn't associate reflection vectors, we should associate cones. And here, the cone associated to this point is the cone defined by these two vectors. So there's a cone, there's a cone, there's a cone here. So points which are non-smooth, we must associate cones. Anyway, so this is the geometry of the reflection of the Skorokhod reflection problem. Right. So I'm going to go back down to one dimension and write another formula for the Skorokhod reflection problem. So this formula was motivated by trying to understand a paper by Dupuy and Hayek, so Bruce Hayek. It's in 1994. It was published in Queuing Systems. And the paper is called A Simple Formula for Mean Multiplexing Delay for Independent Regenerative Sources. So, and the formula was written down in this paper by myself and a couple of colleagues, and it was published in Stochastic Processes and Applications in 97, and it goes like this. In the notation I introduced there, it can be shown that Q of t. Okay, I'm assuming that x of 0 equals 0, so I'll write down the assumptions. X of 0 equals 0 to make things simple, and x continues. And more, bounded variation. So, Brownian motion is not included in this example. We can have things like differences of two increasing Levy processes. So a Levy process with bounded variation, for example, is okay. So, but Brownian motion is not here. So then Q of t can be written as follows, as the integral from 0 to t of an indicator function, and the indicator function inside has Q of s greater than Before I say that, I will write x is bounded variation function, so write x as the difference of two increasing functions. So this is increasing, and this is increasing function. I need that. So decompose that as a difference of two increasing functions. This will enter the formula here. C of t minus C of s, dA of s. Okay, so so this is the formula. If Q of t satisfies the original equation with a continuous bounded variation x, then if I decompose it as a difference of two increasing functions, it satisfies this equation also. So the first thing that you see here is something a little bit weird, in the sense that obviously the first equation does not depend on how I decompose this x. I can add t to both equations, nothing changes, there appears a difference. But then if you add something here, if you increase this and increase this, why should it remain the same? So there's a certain feeling there that something might be wrong. But there is nothing wrong. Indeed, this function this equation is true for any decomposition of x. In particular, it's true for the minimal decomposition as a difference of two increasing functions. Okay, so let's explain this formula. This formula for Skorokhod reflection is somehow a global point of view. This is a more local point of view. So let's think physically. We have a tap here, and I have water coming in. Okay, and then there's water leaking out. Okay, water is leaking out. C of t is the cumulative leak process, if you like, and it's entering according to A of t. Okay, so let's take the droplet point of view, if you like. So the droplet point of view says, if I want to find at time t how much stuff I have here, I must look at the droplets that arrived before time t, so let's say at some point s, and have not left by time t. So a droplet arrives here. Let's think of it as a first come, first serve fluid, if you like. This goes down and will leave at some point of time. It must leave here. Okay. Well, a droplet that arrives here is going to see a fluid level equal to Q of S. So if Q of S is larger than C of t minus C of S, which is the maximum it can go out between time S and t, it will have remained there by time t. Okay, so I'm counting that. So I'm saying, take these indicator functions and add them up, basically, but add them up for s's that are in the support of the arrival measure of the A. It's arriving with respect to it. So do this continuous addition of indicator functions, and that's how you get it. Okay, so so the problem then that I posed is, does the inverse hold? So if I have a Q that satisfies this, does this mean that Q is a Skorokhod reflection mapping? That's the problem. Okay. The answer is, so question. So let's call this star, or actually, let's call this 1, and let's call this 2. Does 2 have a unique solution? If it has a unique solution, it will be the solution of that. The answer that I'm going to present is no, but it has a greatest solution. So if I think of it as a fixed point equation, and I consider all the functions Q which satisfy this equation, there is a greatest solution. There is one that point-wise dominates everything else, and this is precisely the one given before. Okay, so the problem that we faced when we were trying to solve the opposite is that this equation, even though A and C are continuous, does not necessarily have a continuous solution. So there will be solutions that are discontinuous, but the greatest one will be continuous, and in fact will be this one. So I will spend the remaining time in explaining you this, why it is so. Okay, so let's go back and I'll give you actually an outline of the thing, because it involves several lemmas and stuff like that. So let me actually put a star in this equation for the original Skorokhod reflection. So let me call that Q star of t equals x of t plus L star of t, which is x star of t minus the infimum of x of s smaller than t. I don't need to put minimum 0 here because I'm assuming that x of 0 is equal to 0. So that becomes supremum, sorry, there is no x, there is no star, x of t minus x of s for s smaller than t. So the concrete solution of the Skorokhod reflection is called q star of t. And okay, so the first thing I should do is show that q star of t satisfies this equation. Okay, so to show this, there are several ways to proceed. I'm going to proceed using a few lemmas. Let's call this lemma 1, that says that if I take 4 points s, 3 points s prime and t, and if q star of s is larger than c of t minus c of s, then q star of s prime is also larger than c of t minus c of s. Okay. Now, that can be shown directly from the above, but it is, in a sense, obvious if you think it from the physical point of view. It says that if at time s I cannot empty the system by time t, it cannot empty between s and t. That's all it says. It's a triviality. Okay. Lemma 2 says the following, that basically the Skorokhod reflection has a semi-group property. It's a dynamical system. That is, I tell you what happens at the beginning of time, 0. And I apply a certain function, namely this, a functional, to find what happens at time t. Okay? Suppose that at some point of time, s, you have forgotten everything between 0 and s, but you only know q of s. Can you recover q of t? Yes. And the formula is this. Q of t, q star of t, is equal to q star of s plus a of t minus a of s plus, sorry, let me write that as x of t minus x of s, maximum with the supremum of x of t minus x of u for u between s and t. So, so in that sense, if we think of this, we can think of it as a dynamical system because it has a semi-group property. So it satisfies this. And that's true actually for any Skorokhod reflection problem in any dimension. The semi-group property holds. And that's why when x has independent increments, for example, it's a Brownian motion, then q is a Markov process because of this. Okay? Independent increments will imply that that stuff that I put here are independent of the past if I know q star of s, and therefore q star of t will be a Markov process. So that's lemma 2. Lemma 3 says that if I take s between 0 and t again, and if I have q star of s is larger than c of t minus c of s, then q star of s, q star of t is equal to q star of s plus x of t minus x of s. Okay? Again, this is obvious from the above because it says that between time s and t, I have a system that is never empty, and therefore I can forget this and use this equation. So that's lemma 3. So all that is needed in order to basically define the following time. So let's define the time sigma star of t, which is the last s in 0t, such that q star of s is smaller than c of t minus c of s. So in picture, this means that this is time t, this is sigma star of t. This is the last time that you found an empty thing here, and after that it is it's not necessarily increasing. It could go like this. Okay, so by lemma 1, we have that Q star of S is smaller than or equal to C of T minus C of S if S is smaller than sigma star of T, and Q star of S is greater than C of T minus C of S if sigma star of T less than S less than or equal to T. So, so that's what lemma 1 achieves. So we have Q star of S less than that here and greater than that here. And also, by continuity, I have that Q star of sigma star of T is equal to C of T minus C of sigma star of T. So I can write now Q of T using this equation here as Q star of sigma star of T plus x of T minus x of S. Now assume that x is decomposed as a difference of two increasing processes A and C, minus C of T minus C. So this will go away with this, and that will become A of T minus A sigma star of T, which is equal to the integral from sigma star of T to T dA of S. But the interval between sigma star of T and T is precisely the interval of those S for which this holds. So it's equal to the integral from 0 to T. I can put that as an indicator, Q of S greater than C of T minus C of S dA of S. Okay, so that's the proof why Q star satisfies this. It's not the simplest proof, but it's sort of an intuitive proof that leads you to the proof of the opposite. The best, the slickest proof is basically to use Lebesgue-Stieltjes formula for a convex function. So you take a convex function which is of the form, very simple form, x minus c positive part, you stick in Q of T, and then when you take, when you write it as an integral, you have an integral as respect to a first derivative, and then you have some contribution, some sum for the second derivatives, which, you know, a convex function may have points at which the first derivative is discontinuous, and that will show up. And anyway, so there is a way to do that, which is actually written. This other way is written in another paper, in a paper by myself and Günther Last from the Journal of Applied Probability in 2000. And this paper actually generalizes this formula to include cases where we have x to be bounded variation but not continuous, so it can have jumps. And the formula is not that simple. It will have some terms to take into account that have jumps. Okay, so now I'm going to consider the fixed point equation, this fixed point equation. Okay, so let's write the right-hand side as a function, let's call this function theta, of Q. So we have the fixed point equation, Q is equal to theta of Q. Okay, so the first thing that we observe is that theta is an increasing operator. Obviously, if Q is smaller than Q prime, then this interval becomes wider, so it's smaller. So theta is increasing. If Q is smaller than Q tilde, then theta of Q is smaller than theta of Q tilde. Okay, so I have monotonicity, so I can use a successive approximation scheme. I'm going to construct a sequence of functions using just this. Starting from somewhere. Let's start from the largest possible function, q0 equals infinity. If I stick infinity there, then I get 1 here, so q1 is going to be a. Okay. A is smaller than infinity. And therefore, by induction, and because of the monotonicity, you can see that q of k plus 1 is smaller than q of k. So this is decreasing. Decreasing non-negative, and so it converges somewhere. It converges to some q infinity. So that's the definition of a function that we call q infinity. Okay. Now, here is lemma 4, let's call it. If I have a fixed point, so if q is equal to theta of q, then q is smaller than q infinity. Okay, so if I show this, then I have shown half of what I want, because q star is a fixed point. That's what I showed earlier. And therefore q star will be smaller than q infinity, and I will have done half the job. Okay. So the way to show that is, well, q is smaller, is theta of q, then iterate that, use the monotonicity, and then solution will be smaller than q infinity. Okay, that's easy. Now I'm going to define another function. I'm going to define, let's say, I'm giving you this, and I'm going to define the lower functions of x to be, let's say, all increasing L starting from 0 such that x plus L is greater than or equal to 0. So it's all the regulators that I can put there. Now, if I use the L star that I get from Skorokhod reflection, I'm going to get the correct formula. But if we use something else, then we're not going to get something correct. Nevertheless, we can think of that as some object and define the following thing. Let's define, so if I'm going to define a function phi from L of x into L of x in 2 steps. And step 1, I'm going to define the time sigma L of t, which plays the role of sigma star of t I showed you earlier, which is the supremum of all s between 0 and t, such that a of s minus c of s plus L of s. So I'm making a mistake here. I'm using something that is just a regulator, not necessarily the correct one, is smaller than c of t minus c of s. Of course, this cancels with this. Okay, that's exactly the same formula I had used before to define this sigma star of t. So that's sigma L of t, and then phi of L of t is going to be the value of L at this time sigma L of t.
Are you proving the lemma 4 now? I'm just a little bit lost.
I'm not proving anything. No, 4 I just said it can be done.
Step 1 of what?
That's step 1 of the definition. So define phi in 2 steps.
Okay.
And I wrote step 1, and that's step 2. I'm sorry. So that's step 1, that's step 2. Thank you. So it's just a definition. It says this is the cumulative regulator up to the last time. Now this function phi also has a number of interesting properties. The first property it has is that okay, it's not obvious that phi maps L of x into L of x. How do I know that if after I perform, I give you an increasing function L, I define this time, then I take the composition with L, how do I know that phi of L belongs there? So the check that phi of L is actually a member of that. So that can be done. Now, another obvious thing is that phi of L is smaller than or equal to L, because if I increase L, I increase sigma L, and therefore I increase this, because L is an increasing function. So again, we start with an iteration in order hoping to go to the correct one. Okay, so I'll start with some I'm going to define Lk plus 1 equals phi of Lk. And starting with what? Start with L1 equals, so what do I have? I have A minus C plus L, and I want that to be non-negative. So what's an L that achieves that? So I have A minus C plus L. So find an L that makes this thing positive. C. C, right. So L1 equals C.
C.
3C.
Equal C.
Yeah, right. Okay, you can do whatever you like. It doesn't matter. Okay, so let's start with C. Okay, so so I define this. Again, this is decreasing because of this. So it converges to some L infinity. Okay. I don't know what L infinity is, and I don't even know that it is continuous. Okay. So lemma 6 says that L infinity belongs to this class and is continuous. Okay, I'm going to skip the proof of this. The thing to see here is that to prove that it's a member of this class is not hard. To prove that it is continuous, you basically take the set of functions L of k, which is a subset of the set of continuous functions from 0 to infinity, and then you show that they are uniformly bounded and they're continuous, and you use Arzelà-Ascoli to show that this set is relatively compact, therefore its closure is compact here, the limit belongs to the closure, so the limit is a continuous function. So that's what happens here. And lemma 7 says that L infinity satisfies phi of L infinity. Okay, well, again, that requires a little bit of work because I didn't tell you that phi is a continuous function or anything. Therefore, you cannot just put the limit inside. So that takes a little bit of work, but it is true. Okay. Lemma 8 says that L star, the correct one, also belongs to L of x. Okay, we know that. And lemma 9 says that if L belongs to L of x and L is equal to phi of L, so if I have a fixed point of this map, then L is smaller than or equal to L star. So the correct one dominates a fixed point from above. So if I have all that, then the proof becomes trivial and goes like this. So I have Q1. Remember that Q1 was A. I chose Q0 to be infinity. And you told me to take L1 equals C. Okay? So therefore, Q1 plus C is equal to A plus L1. It says A plus C is equal to A plus C. All right? So that's obvious. Now, what do we have? If we take S between 0 and t, we have that Q1 of S is greater than C of t minus C of S. Okay. And that's equivalent to Q1 of t plus C of S, let's write that greater than C of t, which is equivalent to Q. So write the formula for Q1 of t becomes A of S, Q1 of S here, so A of S plus L1 of S is greater than C of t. And if you look at the definition of sigma L, that means that S is greater than sigma L1 of t. Because sigma L1 of t is the largest such that this inequality is violated, therefore S should be larger than sigma L1 of t. Okay, so that's step one. what do we get from this? We get that q2 of t is equal to the integral from 0 to t of the indicator that q1 of s is greater than c of t minus c of s dA of s. Which is, because why? Because I have defined q2 to be theta of q1. That's all I'm saying here. So I'm writing this explicitly. And I'm substituting this set by this. So that will become A of t minus A of sigma L1 of t. Okay. Okay. I should have written another equation here that holds x of sigma L of t is equal to c of t. So this equation is true by definition of L. So if we take this and write it for L1, I will have A of sigma L1 of t plus L1 of sigma L1 of t will become equal to c of t. And so what we're doing now is we are back at the first step. We started from this, we went there, and so we're going to use now this to get something analogous to this and proceed in this manner. So we will keep doing that recursively, and we will arrive at this kind of equations. We will arrive at the equations that qk of t plus c of t is equal to A of t plus Lk of t. And this is true for all k. So I started with a triviality. A plus c is equal to A plus c. That's what it says. I went through the arguments and then show by induction this. Okay? So take the limit as k goes to infinity, and you have that q infinity of t plus c of t is equal to A of t plus L infinity of t. Pointwise limit. All right. Therefore, we have that, what do we have? We have that L infinity is equal to phi of L infinity from this lemma. It is a fixed point. If it is a fixed point, it is smaller than L star. So this is smaller than A of t plus L star of t. And therefore, I have that q infinity of t is smaller than A of t minus c of t plus L star of t, and that's precisely this formula here. That was A minus C. So q infinity is smaller than q star of t. Okay, and because this is a fixed point, it also dominates q star of t. And so we get that q infinity is equal to q star. Okay, so that's the answer to this problem. So what we have here is something that involves several steps. Most of the steps are really basically just properties of monotonicity. There's nothing else here. But it can be quite tedious. So one starts thinking now what is happening in many dimensions. And that's a semi-open problem. Continuing the tradition of semi-open problems from yesterday.
That means you solved it this morning?
No. It means that I know something. I know the proof, but I don't know the formula I'm proving. That's what happens in many dimensions. So a semi-open problem is find an analog of 2 in many dimensions. At least for a canonical Skorokhod deflection problem. So by canonical Skorokhod deflection problem, I mean something that comes from some physical reality like a network that I showed you before. Okay? So it should be possible to take the point of view. I can write Skorokhod reflection, as I told you earlier, with this moving this bug here, is a global point of view. So, but imagine that you watch the particle going from node to node, and think how long it will take to go out and so on, and add these indicator functions and find an analog of this representation formula. Of course, it will be a multidimensional formula, and once you have this formula, you can show that it has a maximal solution, and that this maximal solution is precisely the Skorokhod reflection mapping. Now, I know part of the answer. I know that the formula exists, but the formula is not very pleasing. It's something ugly. And if I use this, I can show that all these steps go through, and the original Skorokhod reflection problem can be recovered in the sense that this formula possesses a maximal solution, a greatest solution, and that's a solution to the Skorokhod reflection problem. But I don't know a simple formula for this. I have no clue. It's quite it's unknown to me. It should exist, but it's unknown to me. Okay, I wanted to. Can I take another 5 minutes just to show some more order-theoretic properties of the? Just very simple. 5 minutes. So what I want to show is that the order-theoretic view of Skorokhod reflection can give you some surprising things. For example, you can say, well, if I think, I'm thinking of time, I'm thinking of functions of time. What is time? Time is a totally ordered set. Okay, so why not make time a partially ordered set? Okay, and that's what is in this paper that I showed you in the beginning, in the paper Order. So, so think of T as an element of a partially ordered set, and in order to make it look like a time, I'm going to assume, so T is a partially ordered set that possesses a least element. So okay, so for example, it could be a tree like that. Something like that. So so that's an example of a partially ordered set. Another example of a partially ordered set is the following: I have a set S, and I have a sigma algebra of subsets of this set. Okay? So I can take T to be this sigma algebra. Okay? So I have functions that are defined on a partially ordered set. So if I think of this case, what's a natural function that's defined on a sigma algebra? Probability. That's not very good because we cannot reflect probability. Probability is positive for most people. I have met people who think probability is negative, but we don't talk to them. It's a signed measure. Okay, so let's think of something that is countably additive over its arguments, but it takes positive and negative values. So let's think of that as a signed measure. So I'm giving you an example of the general theory, if you like, which is basically signed measures. So I want to do Skorokhod reflection of a signed measure. What on earth does this mean? Well, it would mean, let's do Skorokhod reflection on an interval. So remember this interval here, that's the domain, and there is a lower boundary and an upper boundary. Actually, let's call the lower boundary alpha and the upper boundary beta. Okay. So let's take, in fact, these boundaries to be time varying. Well, what does time varying mean here? I have a partially ordered set, so they're functions of this partially ordered set. They are, in fact, functions of this sigma algebra. Okay. And let me assume that they are measures, that they're positive measures. So that's a positive measure, and that's a negative measure. That's a positive measure as well. And let me assume, in order that this is a non-empty interval, that alpha is smaller than or equal to beta. So I have two measures, one is above the other. Okay, so what does it mean to reflect that? Well, it means to find some function L of t and another function U of t, such that the resulting function, lies between alpha of t and beta of t. and such that these things are least, are as small as possible. Okay, and they are increasing. Okay, so I know that this function should be increasing, so they should respect the order of inclusion. That's the correct order in this set. And they should when I add and subtract, they should maintain the function within alpha and beta. So it's surprising that there is a unique solution to that. And not only there is a unique solution, but it is explicit solution. So L of t, L is given as follows. I take alpha, and from alpha I subtract x. So that becomes a signed measure, because that's a measure, that's a signed measure. And I take the positive part of this signed measure. So any signed measure can be decomposed as positive part minus a negative part. It's called the Han-Jordan decomposition. So that's given by this. That's not the component-wise maximum with 0. It's the positive part of the signed measure, and u is x minus beta, negative part. Okay, so it happens that not only I can find a solution, a unique solution, not only the solution is increasing, but it is also additive. There's no a priori reason for these regulators to be additive functions of the argument, but they are. As a matter of fact, I don't use the Han-Jordan decomposition that I told you in order to get this. You can do this directly. And then you can say, well, what happens when alpha is equal to beta? When alpha is equal to beta, you get a zero width lift, if you like. Well, when alpha is equal to beta, L becomes the negative part, and X becomes the positive part, U becomes the negative part. And so you have the Han-Jordan decomposition of the signed measure. So Skorokhod reflection for a signed measure on a zero width interval is equivalent to the Han-Jordan decomposition of it. So this kind of view of Skorokhod reflection can be generalized for an arbitrary partially ordered set with a least element, and you can solve the problem in various cases, and these things can actually be used to give you bounds on some such decompositions, which I don't have time to discuss. There are many interesting examples, but I don't have time to discuss them now. I kept you too long. So, thank you very much.
Quick questions.
You get martingales with partially ordered sets here?
No, I didn't think. I don't like martingales with partial ordered sets. In fact, to tell you the truth, I have an aversion to them.
Yeah, but they might be here.
Yeah, it could be, but I didn't. So when I did partially ordered sets, I did no probability at all. So I didn't think of this as being
but using sigma algebras and measures. With sigma algebras and measures like this, you might run into them.
Yeah. Of course, what I omitted in today's talk completely is the fact that, you know, I can take these formulas and make these objects random and then do probability on top of that, as you did in your mid-90s paper, for instance, and then get some concrete results. For instance, this kind of things can give you easy proofs of the so-called Little's laws or distributional versions of Little's laws, which, when you have systems that are driven by Levy processes, can lead to fixed point equations for Laplace transforms or what have you, which can give explicit results. Not always, but in some cases. So this is, in a sense, this is related to stochastic calculus, but without doing stochastic calculus for these systems.
Very much.
Thank you.